Good morning.
Good morning.
How is everyone?
Morning.
We're
Good.
good.
Nice to hear. Another virtual lecture. Today is April 29, and I am planning to talk today about complex numbers. You covered, as I mentioned that yesterday, you covered complex numbers very lightly. Actually, in one Math 120 course, intermediate algebra course, when you talked about different type of quadratic equations. These numbers are very interesting. There are newest type of numbers in mathematics. They are only something about 200 years older. These are very young numbers in our mathematics. Let me remind you some details which you covered before, because you know what, repetition will never hurt anyone. The one thing what you need to understand, going back into biography of complex numbers, that again, they appeared in mathematics because before they were born, anytime when you were, let's say, using quadratic formula to solve quadratic equations, and as you should be aware of, a quadratic formula method is the universal method for quadratic equations. You can solve any kind of quadratic equation using quadratic formula, because we have other attractive methods for quadratic equations, but they are not universal. Let's say I'm talking about factoring as a method, very beautiful, very elegant way to solve quadratic equations, but it is not a universal, because if that quadratic trinomial representing quadratic equation is a prime, you cannot factor it. And if you cannot factor it, how can you apply, let's say, factorization to solve this method? So again, I'm going to write right now on my paper this equation, but before we do that, let me refer you to your book to see which section and is devoted, and chapter are devoted to that material. And this is section 9.6. And it starts on page 385 and is being continued on pages 386, 387, 388, 389, 390, 391. It is quite a long session, and it is again is being continued on pages 392, where you can see the end of theoretical material at the beginning of exercises and problems. And this is again very interesting material. But I promised you to go back to the beginning point when people started talking about complex numbers. Let's say you need to solve quadratic equation, which comes in its standard form. Standard form is ax squared plus bx plus c. Here, a, b, and c are parameters. They can be positive numbers, they can be negative numbers. B and C even can be zeros. they all belong to set R, set of all real numbers. But you can see, first thing what I wrote down, I wrote A should not be equal to 0, because if A is 0, we cannot talk about quadratic equation. It will be not a quadratic. Just cover that ax squared term by your finger and you can see it becomes linear. But B and C definitely can be separately equal to 0. They can be equal to 0 together simultaneously. In this case, if any of these B or C separately or B and C at the same time are zeros, we just call this like incomplete quadratic equation or incomplete quadratic trinomial. So, and you perfectly know the meaning of word incomplete because it means that something is missing. So, and if let's say we are applying quadratic formula method, I'm going to write down that well-known formula, which we used in this class also a lot. I even showed you 3 different quadratic formulas instead of 1. This is that formula that for many, many, many years, centuries, I would say, if that b squared minus 4ac, which we call a discriminant of that quadratic equation or quadratic trinomial, and which equals to b squared minus 4ac, it is a discriminant of that quadratic equation. If we plug instead of b and a and c their values, we can have 3 different outcomes. And first outcome is about d being a positive number. You have a positive discriminant. What would be the outcome here? You all the time, in this case, will be having 2 not equal to each other equations, x1, let's say, and x2, I will call them x1 and x2, which belong to set R. In other words, in this case, when discriminant is positive, you will have 2 distinct real solutions for any quadratic equation. Second case is we plugged a, b, and c values. We calculated b squared and minus 4ac value, and we got d equals to 0. Discriminant is equal to 0. What can we get out of this value for d when it is equal to 0? In this case, dear ladies and gentlemen, your quadratic trinomial will represent a perfect square, which we definitely can easily factor, and it will be or fitting the formula a plus b parenthesis squared or a minus b parenthesis squared. And definitely you can use quadratic formula, but what you can expect in this case. In this case, these 2 values, x1 and x2, will be equal to each other all the time. I can go even further. X1 is equal to x2, or you can say you have 2 equal real solutions, or you can say that you have 1 real solution, because x1, let's say, will be equal to 10 and x2 will be also equal to 10. And in this case, all the time, these values, matching values for x1 and x2 will be equal to negative b over 2a. I guarantee you that result. And in this case, definitely, x1, x2 matching, or you can just name it like x1 or just x, will be from the set of real numbers. From the set of real numbers. So in this case, you can say that you have one real solution, or you can say that you have two equal real solutions for that equation. So far, so good?
Yes.
Is it coming back from intermediate algebra?
Yes. Yeah.
The last case. The last case is when you are plugging A and B and C values, you square B, subtract 4 times A times C, and you are getting a negative number, which is the value of that discriminant. D is less than 0. It is negative. So what can we get as a conclusion here? For many centuries and many generations, when they were experiencing that value, or when they were dealing with that equation which has that negative discriminant, they were stopping immediately and writing down that there was no solution for that equation. Yeah, it was correct at that time when they were not equipped by complex or imaginary first and complex numbers, but not in our days. Because even in our days, quite often, unfortunately, when we grade papers of our students, we can see that kind of conclusion that discriminant is a negative, there is no solution, which is absolutely incorrect. When we say no solution, we mean no solution at all. What can we say in this case? We can say that there is no real solution. It will be correct. But if you say no solution, it will be absolutely mathematically wrong. This why be extra careful. So what do we have in this case? Yes, we have two solutions, but I'm going to write something and you will understand what I mean. Look what I wrote. I wrote down x1, comma, x2. Can you see I crossed that symbol which is belongs to?
Yes.
How can you explain in words what I wrote down?
They're not real numbers.
Absolutely correct. So which means this what I'm saying. Can we say here that this equation in this case does not have any real solution? Yes, it will be correct because solutions exist, but they are not real numbers. But look what we have. In this case, we have two distinct complex solutions. And this is a new symbol. This is capital C, the first letter of word complex, capitalized and with double leg, as I say. Can you see we have again, or it should be very bold print for that C. So far, so good?
Yes.
And in this case, what would be the outcome? For any quadratic equation with negative discriminant, we all the time will have two distinct complex solutions. You can write it down. And what about this actually complex solution? First, I would like to say about the set of imaginary numbers. It does not have its own symbol, but in my classes, I just have that, you know what, verbal description, the set of all imaginary numbers. Just, you can write it shortly. Because if we use, let's say, capital I, we are using this for the set of irrational numbers. This is why I don't want to have two matching symbols to confuse people, because in this case, they will not know if we talk about the set of irrational numbers or the set of all imaginary numbers. These imaginary numbers, they were born in France. So yeah, definitely they emigrated legally, definitely, to all other countries where they were learning math. This is why they became native in all other countries as well. So, but what kind of numbers? First, we need to start with so-called imaginary unit. Imaginary unit is small case I. It is an international symbol, and it is equal to square root of -1. I equals square root of -1. So this is our imaginary unit. This why it looks very strange, because we are so used to real numbers, and in the real set of all real numbers, we never can square any number or unit. By the way, what is the unit in the set of real numbers? 1. 1 is the unit, because I can write down, let's say 7. Can I write that it is 7 times 1? Yes. Or let's say -2. Can I write that it is -2 times 1?
Yes.
Or let's say +3/7. +3/7. If I like, I all the time can write that it will be 3/7 times 1. So 1 is the unit in the set R, but I is the unit in this set of imaginary numbers, and actually as well as in the set of complex numbers, it is set C. But this is a special, very special unit. After squaring that unit, square of I equals to -1. And before these numbers were born, people could not even dream about anything being squared. I'm talking about anything when I mean what I mean numbers being squared to get actually -1 or any other negative number. This is why when these units and numbers were born, they called them imaginary. But imaginary numbers are, if we deeply think about the meaning of word imaginary, they exist only in their imaginations. Because, for example, let's say I am imagining that I am a Japanese princess. It will be only, let's say, in my brain, in my dreams, because I don't have any connection to Japanese royal family, and I would never have. So this is just exists in my imagination. All actually numbers exist in our imagination in entire math, because nobody can describe the meaning of, say, of number 1 or 2 or 5 or -8. We cannot describe that. But at the same time, we can definitely talk about 1 textbook, 2 students, 3 teachers, $5, or let's say -$1,000, which means I borrowed this money from someone, I need to give it back, and etc. But just to describe or give a definition of, let's say, 1 or 2, nobody can do that, because just this number 1 without the content, one of what or 2 of what kind of items, they do not exist in nature. But at the same time, we constantly operate with these numbers. This why, again, people were confused. But later, when these numbers were born, they were applied at many different fields in our life. They are widely being used in astronomy, in electronics and in other many fields. I'm not even talking about math and physics, of course. So, but it is, again, it is a special unit. It is an imaginary unit. This is why we can talk about a set of numbers where I will be using, let's say I is imaginary unit, and I can talk about 2i or 3/2 of I or negative 0.7 I, etc. This is what I'm doing. You can see, can you see, guys? Or it is dark?
We can see it.
We can see it.
Yeah, I just listed just very few numbers you can see, but I like to ask you to look at what we have in front of each of these I symbols. Did I list these coefficients of I like 2, 3/2, negative 0.7, etc.? Are they real numbers? I'm talking
Yes.
about just coefficients. I'm not talking about number 2i or 3/2 of I or negative 0.7 I. I'm just talking about 2, 3/2, negative 0.7. Are they real numbers?
Yes.
How many numbers do we have in the set of real numbers?
Infinite?
Infinitely many, right?
Yes.
So which means, can I use any of these numbers as a coefficient for I?
Yes.
How many imaginary numbers can we get?
Also infinite?
Infinitely many as well, because I all the time can change a coefficient in front of unit I, right?
Mm-hmm.
This why, can you please write down that you have, in this case, just write this in Word, the set of all imaginary numbers, which comes in the form of yi, you can see I used here set bracket, put here comma, and give a characteristic for each of these components. I will start, or you can put a vertical line, which will be even better. This is very nice modern way to put together that sets. So y belongs to set R, comma, I is square root of -1. This is the set of all imaginary numbers. You can see what I wrote. Y is taken from this set R, which is a set of real numbers. I equals to the square root of -1. In other words, it is an imaginary unit. This is the set of all real, or excuse me, all imaginary numbers. You know what? I will just shortly write set of all image numbers. You can see how I wrote it down in a funny way. Set of all imaginary numbers. So, but the people went further. I would like to discuss with you the meaning of word complex. And can you please give me an example or examples in which we can use word complex, and it can be not just something related to math. I would like to ask you basically to explain me the meaning of word complex. If I start talking, you will be amazed, because definitely we deal with complexes all the time. Okay, do you need my help?
Yes, please.
Excellent. If I say sport complex, what does come to your mind?
I say
That
specific.
I'm saying, let's say, sport complex. What can we have in this course, sport complex? And does it make sense when people hear that word, sport complex? What can come to their mind? Is it some piece of land where we have, let's say, football field and swimming pool and tennis court, and there is a facility for gymnastics and etc. all together in one spot?
Yes.
Is it just one person's opinion? Guys, can you hear me? I asked everyone a question. Can you please reply? Don't forget about class participation grade. I definitely make comments about everything. So please try to get good looking grade for class participation. Okay, can I say a medical complex? Guys?
Yes.
What about shopping malls? Are they complexes?
Yes.
Yes.
Can you see? Can we say that in this case, when we talk about a complex, we mean that it is something like not just very simple, something complicated, but in the nice way, that it has many different things united in one piece, right?
Yeah.
Exactly the same meaning we are using in math. Because when we say complex numbers, what happened here when we started using complex number, we decided to unite in one piece real numbers and imaginary numbers. This is why the formula for the complex number is z which will have real part and imaginary part. This is, again, an international approach, because all the time in my quite long life, and specifically part of the life related to math, I all the time in different countries saw that Z symbol for the complex number. And it is a complex because it has two separately standing parts. One part is real part, the other part is imaginary part, and we united them in one number Z. Is it clear?
Yes.
Yeah.
Yes.
So practically, if we like to describe set C, how it looks, it's a set of all numbers Z. I'm writing right now down and I will show it to you, where X and Y, I did not say Y times I, just X and Y belongs to set R, comma, and I is square root of -1. And I'm going to box it and I will show it to you right now. This is the formula. This is the formula for set C. And now this is the set of all complex numbers. So far, in nowadays, it is the last numerical set in math. I cannot guarantee you that in the near future we will not get any new. I am not a fortune teller, this is why I cannot predict. Maybe yes, maybe it will be for quite a longer time before new type of numbers can appear, but I'm sure that new type of numbers also at one of days in our future will appear in math as well. But so far, set C is the last set in our math. If you like to show this using a diagram So you can see, let's say, set R and separately standing set of all imaginary numbers. And I'm going to shade so if you unite these two sets, which are both shaded, you will get set C. So practically, I can say that set C equals set R, and I can use the union symbol, and with the set of all imaginary numbers. This is what I wrote on the bottom. You can see I used set brackets. It is again an international symbol. R has its own symbol. It is double-legged or bold R. Union, which is from Latin alphabet, capital U, you can see between two sets. C is a set of complex numbers, and it is the union of real and imaginary numbers. But what you see here, and let me call it like formula number one. Formula number one, z equals to zx plus yi, is so-called algebraic form of complex number. Please write it down that it is an algebraic, or in some textbooks they are saying rectangular form of the complex number z. So this is what you actually learned. Let me now show how to build this on our coordinate system. I already sketched x-axis and y, but now I will call them by different names. I am going to call this like, you can see in parentheses. Can you see that R? So this is for only real numbers. I'm talking about horizontal axis. The vertical axis will be only for imaginary numbers. I in parentheses wrote small case I. And if, let's say, I need to show here -2 plus 4i, -2 plus 4i. I need to break this among that plus sign. And what can I say? Can I say here that x here is equal to -2 and y is equal to 4, ladies and gentlemen? Can I?
Yes.
Yes.
So on horizontal line, please find -2 on horizontal line, because it is so-called real part. On that vertical line, go up, because y is positive, 4 units up, 2, 3, 4. Just call it 4, but actually, because it is on imaginary axis, this is 4i. And after that, please, I'm grabbing my ruler to have it more attractive. Find that number z on intersection of two perpendiculars. And this is your z right here. Z is right there. Okay? So, but you know what? Let's do what? Let's connect that point representing Z with the center of that system. And I'm going to use a dashed segment. Does it remind you a little bit of that approach which we used for polar coordinates, guys?
Yes.
Yes. Yes.
Call it R. So it will be R. Looks familiar, I think. And that angle, which we also showed in the polar coordinates, is theta. And right now, with extremely easy math manipulations, I will get right now another form, because instead of Z equals to X plus Y, I will be using, if you remember from the polar coordinate section, X was equal to what? Is it R times cosine theta?
Yes.
Yeah.
Excellent. What about Y? Is it R times sine theta?
Yes.
Yeah.
This is what I wrote down. And now, can you see both addends share R as a common factor?
Yeah.
Yes.
Can we factor it out?
Yes.
Definitely we can. And look what we are getting. R is outside. We have parentheses. We have cosine theta. I like to use a very easy property from a basic operation like multiplication. Do we know that A times B equals to B times A? It is commutative property of multiplication. So instead of writing down sine theta I will write I times sine theta. Do you let me do that?
Yeah.
And look what I'm getting. This is the second form of the same, actually, same number Z, but it is not an algebraic form anymore. Traditionally, actually, we call it trigonometric form. Trigonometric form of the complex number. And I like this better. But at the same time, if we like, can we say that it is in the polar form?
Yes.
Guys?
Yes.
Yes.
Definitely. So you can use that terminology which you like better. So I like better trigonometric form, but trigonometric form or polar form, it is same thing. This what we got already. We have already two different forms. Today I will not be showing you the other form, which is an exponential form, and I need to talk about Euler's formula, de Moivre's formula. I definitely will explain you everything, because for you it will be a new material. Algebraic form is not a new material, but two other forms are. But I really like to show you an amazing property of powers of I, unit trigonometric, of the imaginary units power. It has a magical property. First thing, you have on page 386 that property, but I promise that I show that in the form which is mathematically much more elegant than your book has. Let's see what is going on. I will start with very easy powers of I unit. I in the first power, is it I?
Yeah.
I in the second power, we already wrote it down. Is it -1?
Yes.
I in the third power, is it second power multiplied by first power?
Yeah.
If you multiply results of these powers, which is -1 for the second power and I for the first, is it -I?
Yes.
I to the fourth power. How can we treat that? Oh, in many ways. But the best way is probably square of square. Is it true?
Yeah.
What I squared was -1. If you treat fourth power like square of square, it will be result of I squared, which is -1, which should be squared. Is it +1?
Yeah.
And look what I doing. I showed you this in the box. I wrote it down. I to the first is I to the second is -1, I cubed is I to the fourth is +1. Up to you to write this +1 or just 1, up to you. Can I continue?
Yes.
I would like to ask you very kindly to find the results of the following powers. I to the fifth power, I to the sixth power, I to the seventh power, please write it down on your paper, I to the eighth power. Please, I will give you some time, just a little bit, to proceed to find these values, but please don't stop here and continue with another cycle. Let's say I to the 9th, I to the 10th, I to the 11th power, and I to the 12th power. Enough. And I really like to see what you get. Let's start with the first four, this second group of 4 powers, starting with I to the 5th, ending with I to the 8th. Can you please write down their values? While you do that, I will check attendance. Andrew? Andrew?
He says he's here, but he doesn't, his mic doesn't work.
This one, I see his name. I just do not understand if there are microphones not working. And Tima, and I saw her name also. Okay, Lorraine?
Here.
Lynn?
Here.
Juanita? Okay, Yuran?
Here.
Gabriel?
Here.
Divina?
Here.
Chantal?
Here.
Okay, Gongsi?
Here.
Kyle?
Here.
Matthew?
Here.
Julian?
Here.
Nathan?
Here.
Alejandra?
Here.
Dear Nathan, I need to apologize because of the technical problem yesterday. You probably, if anyone watched the video for yesterday's lecture, I started the class, and after that, unfortunately, it started showing your picture, because on the top, I see pictures of my students here on the screen. I did not do that purposely. This Zoom did it without my permission. I really deeply apologize. Can you accept my apology?
Yes, it's all right.
Thank you. But again, I did not do anything purposely. It was done against my will by Zoom. Okay. Guys, I would like to hear from you. Okay, what did you get for I to the 5th?
I.
Accepted. For I to the sixth.
-1.
Also accepted. For I to the seventh. I to the 7. Can I say that it is the fourth power multiplied by the third power?
Yeah.
If you multiply their values, what do you get? It will be 1 times -I. Is it -I?
Yes.
Yeah.
And 8th power, is it square of 4th power?
Yeah.
So it is 1. And you can see, I wrote it a long time ago already. Can you see? You have another cycle, and you can see absolutely matching values. They match values of these powers in the first box, right?
Yeah.
And let's finish with the third, four powers. I to the 9, up to you. Can you treat this like 8 power times first power? Guys? Yes, no?
Yes.
I
Yeah.
said 8 power times first power. So it is I, because it is 1 times I. I to the 10th. Can I treat, let's say, this like I to the 8th power times I squared?
Yeah.
So it will be +1 times -1. So it will be what? -1. And so on. You can, again, why I'm using mainly right now here, let's say 8, because it was easy. But if I like to do, let's say 11th, 11th power, can I say that it is a 10 power times first power? In this case, I need to multiply -1 by I, and I'm getting -I. I to the 12th. Oh my God, I can treat this in many different ways. Let's say 6 power squared, which will be -1 squared. Or if I like, I can say that it is a cube of the 4th power, and etc. You can use different modifications. Or let's say 8 power times I to the 4th power. Doesn't matter what you use. You just need to give that version which has exponents added, giving us 12. So, or if you use power to the power, let's say cube of the 4th power, 4 times 3 is 12. So in this case, it will be value of the 4th power, which is 1, raised to the 3rd power, 1 cubed is 1. And you are getting another cycle. And you can see we have same values over and over and over, which are I, -1, -I, +1, and again, I, -1, -I, +1. Agree?
Yes.
Now let's create a formula. And I'm going to write right now something which looks much better than what you have on your textbook on page 386. Can you look at 4th power, 8th power, and the 12th power? Can you see they're all equal to 1?
Yeah.
What about these numbers, 4, 8, and 12? Are they multiples of 4?
Yeah.
Voila. I can write down that I to the 4k. 4k is an exponent, and 4k, when we write 4k, we mean these are numbers which are multiples of 4. All the time, it will be 1. I to the 4k will be equal to 1. If you have I to the 4k plus 1, the answer will be I. If you have I to the 4k plus 2, the answer will be here, -1. And finally, if you have I to the 4k plus 3, the answer all the time will be -I. I will show you this box right now. I to the 4k is 1. I to the 4k plus 1 is I to the 4k plus 2 is -1. And finally, I to the 4k plus 3 is -I. And let me show, did you have an opportunity to write it down? Guys, I'm confused. I don't know what to do right now. Are you done with this last
Yes.
box?
Yeah,
Yeah.
we're done.
Thank you. How to practically use it easily? Let's show examples. Example number 1. I, let's say, to the 93rd power. I to the 93. What should you do? You need to precisely look at this 93. Which number closest to, definitely it should be smaller than 93. Closest to 93 is divisible by 4. Guys, which number closest to 93 is nicely divisible by 4?
92.
Absolutely, yes. Look what I'm going to do. I will write I to the 92 plus 1. Is it matching right now? I to the 4k plus 1.
Yes.
Because 92 is a multiple of 4. What would be the answer here? What do you
I.
have for I to the 4k plus 1? Is it I?
Yes.
Yes.
That's it? You solved the problem. Another example. 2. I to the negative, let's say, 23. I to the negative, oops, I wrote the I to the negative, it will be the last one, negative 23. First, I don't want negative power. I will convert this into 1 over I to the positive 23. Now, which number closest to 23 is divisible by 4? Is it 20?
Yes.
So look what I did. I'm writing 1 over I to the 20 plus 3. Is it fitting 4k plus 3?
Yeah.
So it will be 1 over negative I. But we never leave irrationalities, irrational numbers in denominators, and we never leave I units or complex form in the denominator. This is why I am going to multiply top and the bottom by I on the top, I on the bottom, and proceed, because now it will be 1 times I. 1 times I is I. On the bottom, we have negative I squared. Negative I squared. Negative sign. But what about I squared? Is it negative 1?
Yes.
I'm replacing this by negative 1. So on the bottom, I have minus negative 1. Is it positive 1?
Yeah.
On the top, I had I. So the answer here is I. You can see here, we have a little bit longer process. But this important box, I'm placing many arrows here, is very important. If you know this value, so again, if you have powers like with exponents multiples of 4, it is answer 1. Multiples of 4 plus 1, it is I. Multiples of 4 plus 2, it is here negative 1. And multiples of 4 plus 3, answer will be negative I. That's it. I will definitely continue probably and tomorrow and even on Friday also with this material because it is quite big section. And here again, all materials, specifically Euler's formula, Moivre's formula, applications of this material is quite challenging, but you need to know that and for physics course and for calculus courses, for electronics, astronomy, and for many other fields as well. I hope that we can finish right now our lecture. I apologize for keeping you a little bit longer, unfortunately. So do you let me go?
Yes.
Yeah.
Thank you for being here. Everyone have a nice, beautiful day and stay safe and healthy. Okay?
Thank you.
Goodbye.
Bye.
Bye-bye.
Bye.